Welcome back to AI.Code.Cast. Today's daily challenge problem uh, might have you scratching your head a bit. It's all about rotating a box, and then we have to simulate the effects of gravity.
Yeah, and what I think is so fascinating about this one is how it makes us think outside of just like algorithms and consider the physics of, how objects would move within a confined space.
Totally. And you've given us some resources on the rotating the box problem, and we're going to unpack the different approaches. So to start, picture a box viewed from the side. It's represented as a grid, and we're going to mark empty spaces with a period, stones with a hashtag, and unmovable obstacles as an asterisk.
Okay, and then imagine we're rotating this whole box 90 degrees clockwise, and those stones, unless there's an obstacle in the way, are naturally going to fall to the bottom due to gravity.
Okay, so I'm picturing this in my mind.
Okay.
So our task is to figure out the final arrangement of all these elements after we rotate it and after gravity does its work.
Exactly, and the real challenge is how to code this efficiently. Like a simple solution might work, but it could get really slow if we have a really big box, computationally speaking.
Right. Okay, so let's start with the most straightforward approach, what people often call the brute force method. How would that work?
So the brute force approach, it's pretty intuitive. First, we rotate the whole grid as the problem tells us to. Then we go row by row, and we simulate gravity for each stone.
Okay, so like if a stone has an empty space below it, we move it down, right?
Exactly. And we repeat this for every stone in the row.
Yeah.
Then we move to the next row down and do the same thing, and we just continue down the box until all stones have settled as far down as they can go.
Sounds simple enough, but I'm guessing there are some drawbacks to this approach.
You're totally right. The simplicity comes at a cost, and that's efficiency. So imagine an empty space that's like near the bottom of the box. With brute force, we might have to scan the whole column above that empty space just to see if there's a stone that might fall down.
Ah, I see. So that could lead to a lot of extra work, especially for larger grids.
Exactly. So for each empty space, we might have to scan a whole column. That back and forth checking, that really slows things down.
Okay, so the brute force method, it's easy to understand, but maybe not the fastest way to solve this.
Right. And even before we move on to more optimized solutions, it's important to see the potential pitfalls with this basic approach.
Okay, what kind of pitfalls are we talking about? What should coders watch out for?
Well, a common mistake is forgetting to process the grid in the right order. You have to rotate the entire grid first before you apply the gravity simulation.
Okay, that makes sense. Rotating first, make sure we're working with the correct orientation before simulating gravity.
Exactly. And another one is mishandling the obstacles. So stones can't pass through obstacles, right? They got to stop on top of them, like hitting a wall.
So when we're simulating gravity, we always have to check if there's an obstacle below a stone before we move it down.
Exactly. If you ignore the obstacles, then stones could, pass right through them, and that breaks the rules of the problem.
Gotcha. Okay, these are really helpful points to keep in mind. Now, I'm curious um, about how we can speed up the process. What's the first step towards optimizing our solution?
Well, the key here is to cut down on all those extra column scans that we talked about. Instead of checking every space above an empty one, what if we knew exactly where a stone would land?
That's interesting. Is there a way to, like, track the lowest empty space in each column so then when a stone needs to fall, we could just drop it right there without checking every space?
You're on the right track. What if we could mark that lowest empty space somehow? So when a stone needs to fall, boom, we know exactly where it goes.
That would definitely speed things up. But how would we keep track of those lowest empty spaces efficiently? It feels like we'd still need to scan the columns to find them in the first place.
That's where a clever technique comes in. We can use what's called a pointer to help us.
A pointer. Can you explain what that means in this context? I don't quite see how a pointer would help.
Okay, think of it like a librarian who's using their finger to point to the exact book you need on the shelf. In code, a pointer does something similar. It points to the memory location of a piece of data.
Okay, that makes sense. So in this case, our pointer would point to the lowest empty space in each column.
Exactly. So instead of searching for that lowest empty cell every time, we use the pointer to remember its location. It's like putting a sticky note on that space so we can find it instantly.
I'm starting to see how this could work.
Yeah.
So would we have a pointer for each column, and would they all start at the bottom row?
Precisely. We initialize our pointers to point at the bottom row. Then, as we process the grid, we adjust those pointers depending on where the stones and obstacles are.
All right, so let's dive into how these pointers would work. So we've rotated the grid, and we've got our pointer set up. What happens when we come across a stone?
Okay, so we encounter a stone. We look at the pointer for that column, and the pointer is already telling us the lowest empty space in that column.
So we can just move the stone straight down to the row that our pointer is pointing to, right?
Exactly. No need to check every space along the way. And after we place that stone, we update the pointer.
Right, because that space isn't empty anymore. We had to move the pointer up to the next empty space in that column.
You got it. So the pointer is always adjusting, always pointing to the next available spot for a falling stone.
This pointer idea is really clever. But what happens if we find an obstacle? Do those mess up our pointers?
Well, obstacles are like roadblocks for our stones. When we hit an obstacle, we have to reset the pointer for that column. The obstacle basically creates a new bottom for that column.
So any stones above the obstacle can only fall as far as that obstacle.
Exactly. We update the pointer to point to the row right above the obstacle. That way, any stones above it will stop right before hitting the obstacle.
Okay, that makes sense. So the pointer is always showing us the lowest available space, whether it's at the actual bottom of the box or at the top of an obstacle.
You got it. Now, I have a question for Nano. What if there aren't any stones in a column? What does the pointer do then?
Let me think. If a column is empty, or maybe only has obstacles, then the pointer wouldn't really need to move, would it? It would just stay at the bottom row, showing that there are no stones to fall in that column.
That's exactly right. The pointer stays put if there's nothing for it to track.
This pointer approach is a really neat way to optimize our solution. We got rid of all that scanning and streamlined the gravity simulation.
And we're just getting started. We still need to talk about how we actually implement all this. And then there's an even more elegant solution out there, one that combines the rotation and gravity into one step.
Now you've got me really curious. I can't wait to learn more about these advanced techniques. But before we do that, I think it's worth talking about why this seemingly simple problem of rotating a box is such a big deal for technical interviews.
That's a great point. This problem might seem kind of abstract at first, but it actually touches on a lot of really fundamental concepts that are super important in software development. Maybe we can dive into that after a quick break.
Welcome back to AI.Code.Cast. Before the break, we were really starting to see all the insights we can get from this rotating the box challenge.
It's true. It's a problem that seems so simple at first, but it can tell you a lot about how someone solves problems, and if they understand basic programming ideas.
Like, for example, it shows how important data structures are. Representing the box as a grid, like a two-dimensional array, is something you see all the time in programming, especially when you're working with visual or spatial data.
Exactly. That kind of data structure is everywhere, from image processing, like think Photoshop, to video games, to maps and simulations, all kinds of stuff.
So by working with a grid in this problem, we're not just solving this one challenge, we're learning skills that can be applied to a ton of different things.
Exactly. And beyond just data structures, this problem also makes you think about how to break down a complex task into smaller, more manageable steps. Remember how we approached it? We started with that basic brute force method, saw what was wrong with it, and then, step by step, we made our solution better and more efficient.
Right. That whole process of breaking down a problem, analyzing it, and then finding ways to optimize it, that's what software development is all about.
It really is. And people who interview programmers, they love to see that someone can think that way. It shows they can take on big, complicated projects by dividing them into smaller, more manageable chunks.
So even though we're just playing with this idea of rotating a box, the skills we're using are super relevant to real software engineering work.
Absolutely. Now let's circle back to that optimized solution that uses pointers. We've talked about the concept, but I'd love to see it in action. Can you walk me through how we would actually make this pointer magic happen?
Sure. Let's break it down. First, we do the same thing as in the brute force approach, rotate that box 90 degrees clockwise.
Got it. Rotate first, gravity second.
Now for the fun part, the pointers. We make an array of pointers, one for every column in our rotated box. Each pointer starts out pointing to the very bottom row. That's where a stone would land if nothing was in the way.
So it's like we're setting these pointers up as markers for the lowest open spots in each column.
Exactly. And now we look at the rotated box, column by column, from left to right. And in each column, we'll find three kinds of things: stones, obstacles, and empty spaces.
And what we do will depend on what we find, right?
Right. Let's start easy. Empty spaces. If we find an empty space, we don't do anything. Our pointer is already pointing to the lowest open spot. There's no stone to move, so we just keep going.
Makes sense. Empty spaces don't affect the gravity, so we can ignore them.
Okay, so what about when we find a stone? This is where the pointer shines. We grab that stone and move it straight down to the row that our pointer is pointing to.
So we put the stone exactly where it needs to be without having to check the entire column, right?
Exactly. And once we've placed it, we have to update the pointer.
Right.
That spot isn't empty anymore, so we bump the pointer up one row to point to the next open space.
So it's constantly adapting, showing us where the next falling stone should go. What about when we hit an obstacle? How do those work with the pointers?
Obstacles are a bit trickier, but our pointers can handle them. Remember, stones can't go through obstacles, so when we hit one, we got to reset the pointer for that column.
Reset. What do you mean by that?
Well, it's like the obstacle creates a new bottom for that column. Any stones above it can only fall as far as that obstacle, right? So we move our pointer so it points to the row just above the obstacle.
Ah, okay, I see. So the pointer acts like the obstacle is the new bottom of the column. So
Yeah.
stones will fall down and stop right before they hit it.
Exactly. By resetting the pointer like this, we make sure our simulation is doing things right, keeping the stones from going through the obstacles.
Okay, the logic is making sense. The pointer is always showing the lowest open space, either at the very bottom or just above an obstacle.
You got it. Now, what about when we get to the very top row of a column? Do we need to do anything special with our pointer there?
Not really. When we reach the top, we're basically done with that column. Any stones that were higher up would have already fallen because of gravity, and our pointer should be in the right spot in case any new stones fall into that column when we rotated everything.
Okay, so everything works out perfectly with these pointers. Seems way more efficient than just brute forcing it.
It definitely is, and the cool thing is, it's not that hard to code. You're basically going through the grid just once, looking at what's in each cell, and updating your pointers as you go.
So no more nested loops and checking entire columns over and over.
Nope. We got rid of all that extra work with this smart pointer strategy.
This optimized solution is pretty impressive. It shows how important it is to use the right tools and techniques to make our algorithms faster.
You said it. Now, before we get to the big finale, there's one more thing I want to point out about this optimized approach. Even though it's way faster than brute force, it actually has the same time complexity, technically speaking.
Wait, really? I thought the optimized way was definitely faster.
It is faster in practice, but when we talk about the theoretical time complexity, we use something called big O notation. And in big O terms, both brute force and the optimized approach have a complexity of OMN, where M is the number of rows and N is the number of columns.
So the optimized approach is faster in real life, but it has the same big O complexity as the brute force method.
Yep. That's because both methods end up looking at every single cell in the grid once. But the optimized way does a lot less work for each cell.
Ah, okay. So even though both methods have the same big O complexity, the optimized one is doing less work overall, which makes it faster.
Precisely. And in real-world situations, doing less work can make a big difference, especially when you have huge amounts of data.
That makes a lot of sense. Okay, so the optimized way is faster in practice, even if its big O is the same as brute force. Now, I'm really excited to hear about that single-pass solution you mentioned, the one that does the rotating and the gravity all at once. How is that even possible?
We'll hold on to that excitement. We'll uncover the secrets of that super elegant solution after a quick break.
Welcome back to AI.Code.Cast. We've gone from brute force to optimized pointers, and now we're ready for the grand finale, the most elegant way to solve rotating the box.
This single pass solution, it's all about efficiency. We're going to skip rotating the whole box and just figure out where each element will end up after the rotation and gravity happen.
I'm intrigued. Skipping the rotation step sounds impossible. How does that even work?
It's all about mapping coordinates. Think about what a 90-degree clockwise rotation does. Rows turn into columns and columns turn into rows.
Right, that's the basic idea of rotation.
So let's say we have an element at position, ij, in our original box. I is the row, A is the column. After a 90-degree rotation, where do you think this element will land?
Let me see. It seems like it would be somewhere in column I of the rotated box, but I'm not sure about the exact row.
You're getting there. With a little geometry, we can get a formula to find the exact spot. The element at ij in the original box will end up at j of I1 in the rotated box, where m is the number of rows in the original box.
That's a cool formula. But how does gravity fit into all this?
That's the best part. We use this formula to put elements right into their final spots in the rotated box, thinking about gravity as we go. It's like we're predicting where each element will end up.
So we're not rotating the whole box first. We're taking each element, and using this formula to put it directly in the right place in the rotated box, accounting for gravity along the way.
You got it. And like with the pointers, we'll still use pointers to track the lowest open spot in each column of the rotated box.
So we're combining pointer logic with this coordinate mapping idea.
Exactly. Here's how it works. We create an empty rotated box. Then we look at each element in the original box, row by row.
So we're going one by one, using the formula, and thinking about gravity as we place each element.
Exactly. Now, if it's an obstacle, we just put it directly into its spot in the rotated box based on the formula. Obstacles don't care about gravity, so they're easy.
They're like the fixed points in our rotated box, always staying in the same spot.
Now, when we find a stone, that's when we think about gravity. We check the pointer for that column in the rotated box to see where the lowest open space is.
Just like before, the pointer tells us where the stone should fall.
Right. We put the stone there and then move the pointer up one row, same as we did before.
So this single-pass method handles rotation and gravity all at once. It uses that coordinate mapping formula and our helpful pointers.
And what about the empty spaces? We ignore them. They'll get filled in as stones fall down into them.
The single-pass method is so efficient. I'm amazed at how it simplifies everything. But is it that much faster than the optimized pointer approach?
In terms of big O complexity, they're both OMN, but this single pass method might be a tiny bit faster because we don't have to create and work with a separate rotated box.
So it's saving time and memory by doing everything in one place.
You got it. This single pass solution, it's the definition of elegant code. It's clean, efficient, and shows a real understanding of the problem.
We've come a long way from that simple brute force method. We started with a basic approach, saw where it could be better, and step by step, we improved our solution. That's a process that's useful not just in coding, but in all kinds of problem solving.
Absolutely. And the things we've learned today, data structures, breaking problems down, efficiency, using pointers, those are all super valuable skills for any programmer to have.
This has been an awesome deep dive into the rotating the box challenge. We've explored different approaches, talked about their strengths and weaknesses, and learned how to think critically about optimization. I'm leaving with a much better understanding of how to write elegant code and how to always look for ways to make my solutions better.
And that's the beauty of coding. There's always something new to learn, always a way to improve. Thanks for joining us on AI.Code.Cast. Keep practicing.